Hello Matrix. Welcome to the second of 4 pre-grade 12 sections of Analytical Geometry. Remember, pause the video at any time, either to rethink a concept or slide, or to check your solutions. Pre-grade 12 sections. So far, we have done formulae at the angle of inclination, and we're now about to do graph concepts. Axis-intercepts, equations, shapes, points on graphs, and very important, points of intersection. Thereafter, equations of straight-line graphs and quadrilaterals. When we think of graphs, we think y equals mx plus c and various rote procedures. Let's rather think of graph concepts in general. 5 basic facts about graphs. In fact, about all graphs. First of all, axis-intercepts. Given the equation of any graph, since every point on the y-axis has an x-coordinate equal to 0, we substitute x equal to 0 to find the y-intercept or intercepts. And since every point on the x-axis has y equal to 0, we substitute y equal to 0 to find the x-intercept or intercepts. See the points on the sketch, where we could understand that every single point on the y-axis would have an x-coordinate of 0, and nowhere else would there be a point with an x-coordinate of 0, and every point on the x-axis would have a y-coordinate of 0, and nowhere else but on the x-axis would you find a point with a y-coordinate of 0. The equation of a graph is true for all points on the graph. It is the condition obeyed by all points on the graph. And so the equation of the y-axis is x equal to 0, because that is true of all points on the y-axis. And the equation of the x-axis is y equals 0. Again, that is true of all points on the x-axis. Shapes of graphs. Different shapes are indicated by various equations. For example, y equals mx plus c indicates a straight line. X squared plus y squared equals r squared indicates a circle. You don't know that yet. And why would it? If you just have a look at the little sketch on the side here, and consider that point xy, which could in fact be placed anywhere on the edge of the circle, true of that point, no matter where it is, would be that the sum of the squares of x and y would be equal to the square of r, according to the theorem of Pythagoras. And that is exactly why that is the equation of the circle, because it is true of every single point. We also recall algebraic graphs, parabolas, hyperbolas, and exponential functions. So, in considering points on graphs, it follows that if a point lies on a graph, the equation is true for its coordinates, i.e. the coordinates of the point satisfy the equation, so we substitute. And conversely, if a point, i.e. its coordinates, satisfy the equation of a graph, i.e. makes it true, then that point does lie on the graph. Pause while you work through worked example 1 below. Pause again to check your answers. Since A, in the first place, is the x-coordinate of that point, we replace x by A in the equation to find A. And since in the second example, A is the y-coordinate, we replace y by A to solve for A in the second question. Does the point 4, 3 lie on the graph? X minus y plus 1 equals 0? Well, for x equals 4 and y equals 3, the value of x minus y plus 1 equals 2 and not 0. Therefore, no, it doesn't lie on the graph. Note, there's no need to rewrite this equation in standard form. It remains a condition, and the point 4, 3 does not satisfy this condition. What about points of intersection? Points common to both graphs. The coordinates of the points of intersection of two graphs obey the condition of both graphs. It must be that. They must satisfy both equations simultaneously. Simultaneously means at the same time. These are either found algebraically by solving the two equations or graphically by reading from the graph. Now, pause and have some fun with the following worked example. Pause again to check your responses. Could you think of points xy for which xy equals 6? Could you think of points xy for which x plus y equals 5? And can you now think of a point or points for which they will be satisfied simultaneously? In other words, the product of x and y will be 6, as well as the sum of x and y being 5. Were you able to illustrate your findings graphically? And now, algebraically, could you confirm your results by solving the two equations simultaneously? Now try worked example 3 and pause to answer this question. Pause to check your answer. Once again, simultaneous equations, meaning they have to be true at the same time. And so when solving the equations, we found the point -2, 3. Did you think of checking your answer by yourself first? By substituting x equal to -2 into this equation, we find that y equals 3, which is correct. And putting x equals -2 into this equation, y equals -2, which is +2 plus 1, which is also equal to 3. Therefore, both equations have been satisfied by the solution. And also see that the solution makes sense on the sketch. The x-coordinate of P being -2, yep, that looks reasonable. And the y-coordinate of P being 3, yes, that is also reasonable. Thank you for listening to these important general graph concepts. In the next video, we will apply this thinking to straight line graphs and later on to circles. Be inspired as you develop a simple, logical approach to analytical geometry.
Check out the video description below for practice questions from our study guides. If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from the Answer Series, your key to exam success.